Hello everyone, so we're from S15 Group 2, and in this video we're going to present our maths assignment. So the first task is the growth population in Canada, and the second task is numerical method. In this first task, we're going to talk about the population growth in Canada from 2005 to 2025. The main focus is the application of first order differential equation to the population in Canada from 2005 to 2025. In 1798, Thomas Malthus, an English clergyman, scholar, and economist, developed a fundamental concept for modeling and analyzing human population. So in this task, we're going to use the Malthusian model to find the population growth in Canada from 2005 to 2025. So the Malthusian model assumes that the rate of population growth in Canada increases at a given time is proportional to the number of population at that time, where the Malthusian model can be written as dp over dt equals kp, where pt is the number of population at time, years, and k is the constant of proportionality. There are four main objectives of this task. First and foremost, we use the Malthusian model to find the total population in Canada from 2005 to 2025. Then we use the model to predict future values after 2025. Then we use the model to predict past values of population in Canada before 2005. Last but not least, we identified the reasons why the total number of populations in Canada is not exact to the data recorded.
This is the table of data population for Canada, and this is the graph population in Canada.
Okay, so let's define PT. This represents the number of individuals in a population at time t, where t is measured in years. We're told that the rate of change of the population is proportional to the size of the population itself, which means dp over dt is equals to kp, where k is the constant of proportionality. K can be either positive or negative depending on whether the population is growing or shrinking. First, we solve the equation by using separable variable by first separating the variables p and t. So we got 1 over p dp is equals to k dt. Then we integrate both sides. So we got ln p is equals to kt plus c. Then we exponentiate both sides. So we got p is equals to exponent kt times exponent c. So we let a is equals to exponent c because exponent c is a constant. Therefore, we got the general solution can be simplified as p is equals to a exponent kt. Using the initial condition where t is equals to 0 on 2005, while p is equals to 32,215,916, and we sub them in the equation. So we got a is equals to 32,215,916. Therefore, the general solutions become p is equals to 32,215,916 exponent kt. Then we also find k constant by using t is equals to 1, which on 2006, while p is equals to 32,531,867. Then we sub them in the equation. So we got 32,531,867 is equals to 32,215,916 exponent k bracket 1. So we arrange that to get the value of k, which is 0.0097595. So we got the particular solutions, which is pt is equals to 32,215,916 exponent 0.0097595 t.
This table shows the particular solution of Canada's population from 2005 to 2025. The time column represents the number of years since 2005, where 2005 is time equal to 0. Each row match a specific years with its corresponding population. The data demonstrate a steady and continuous increase in population over the 20 years period, from about 32.2 million in 2005 to over 39.1 million in 2025, supporting a consistent growth trend that may be modeled by a mathematical function such as exponential growth. graphs shown illustrate the particular solution for Canada's population growth using a mathematical model. The upper graph represents an exponential growth curve, indicating how the population increased more rapidly over time. This curve fits the nature of the original data, where each year the population rises at a growing rate. The lower graph is a zoomed-in view focusing on a smaller interval of data. This makes it easier to observe the final detail of how the population increased year by year. Together, this graph visually confirms the trend observed in the data table that Canada population is not just increasing, but doing so in a way that can be modeled with a particular mathematical function, which is exponential growth curve.
For the past value, we calculated it for 10 years back, which is 1995. We inserted negative 10 into the particular solution formula and obtained the value. Then, we calculated the percentage error and got 8.43%. We also calculated the future value for 10 years in the future, which is 2035. We substituted 10 into the formula and obtained the value.
Wait, so let's get to the analysis and discussion. So, what has affected the population growth in the past? There are three factors that may be the reason. First one, we have global events. For example, there's war, climate change, and also political instability in other countries that have pushed more people to migrate to Canada. For example, the Syrian refugee crisis on 2015 to 2016 brought many newcomers to Canada. Okay, so there's also immigration, which Canada welcomes hundreds of thousands of immigrants each year due to its immigration-friendly policies. Okay, so lastly, we also have the economic conditions. Economic booms, like oil booms in Alberta, attract more people, while economic downturns, like the 2008 financial crisis, can slow immigration and family growth.
To sum up, we managed to apply first-order differential equations into practice. By using the multivariate model, we were able to achieve all the objectives. While our calculations came close to real values, there were some slight values that didn't quite match with the recorded data, which made sense since there were real-world factors such as policy changes, healthcare improvement, and migration. Overall, this task has helped us to connect maths with the real world and not just show us how to apply first-order differential equations, but shows us why it matters and how powerful it can turn numbers into insights.
For task 2, which is numerical method, we use TRAPEZIUM rule. And the questions, the functions given, ln x cubed plus 5x squared from x negative 4 to x negative 1 by using TRAPEZIUM rule with 5 and 9 subinterval. And the final answer will be in 6 decimal places. Then we go to the calculations. Firstly, we must find h, which is b minus a, and then divided by n. So negative 4 minus negative 1 divided by 5, and then we got 0.6 for h. Then for s, we put negative 4 to negative 1. And then for fx, we put from the equation, which is ln x cubed plus 5x squared. And then for coefficient, we substitute accordingly. Then we find coefficient multiplied with fx, and we sum up the number, and we got 9.04068. And then for area of the graph from negative 4 to negative 1, we use the equation h over 2 multiplied with c coefficient multiplied with fx. And then we got 2.712206.
So for the 9 subinterval, first we find the value of h, which is b minus a over n, and we get 0.333. And next we substitute the value of x equals to negative 4 until x equals to negative 1, and we insert the equation ln x cubed plus 5x squared, and we just insert the coefficient accordingly. And for the next table, we find the value of coefficient multiplied with fx, and we sum it up, and we get 16.4427. And for the value of area of the graph from negative 4 until negative 1, we just take the value of h over 2 and multiply with the total sum that coefficient multiply with fx, and we get 2.7404. So this is the graph of our fx from -4 until -1. Next is the percentage error. For the 5 subinterval, 2.7536 is the actual value and 2.7122 is the value that we get from Excel. So after we minus and multiply with 100%, we get the percentage error is 1.5%. For the 9 subinterval, the value that we get from Excel is 2.7404. So the error is 0.5%. In conclusion, we successfully found the total area approximation for both graph using trapezium method. For the 5 subinterval is 2.712206 and for the 9 subinterval is 2.740442. We can conclude that the 9 subinterval are more accurate because of error decrease with smaller width, which is H.